Before World War II ended, engineers believed aircraft speed had reached a natural limit. As planes approached transonic speed, drag exploded, control degraded, and performance collapsed. More power only made the problem worse. Richard T. Whitcomb proved that the barrier was not the engine, not the pilot, and not the materials. It was the shape of the air itself, and he figured out how to redesign it. By the early 1940s, aircraft designers were facing a problem they could not explain with existing theory. Engines were becoming more powerful, structures stronger, and manufacturing more precise. On paper, performance should have continued to improve. Instead, aircraft began to behave unpredictably as they approached higher speeds. Pilots reported sudden increases in drag, loss of control effectiveness, and sharp rises in fuel consumption. Aircraft that performed reliably at lower speeds became unstable without warning. Control surfaces responded sluggishly. Structural loads increased dramatically. Engineers labelled this phenomenon drag rise, but the label did not explain the cause. It only described the failure. Attempts to solve the problem followed familiar logic. Designers added engine power. Wings were made thinner. Surfaces were refined. These changes produced minor improvements, but the core limitation remained. In some cases, more power made the aircraft harder to control and more dangerous to fly. The faster designers pushed, the worse the behavior became. The limitation was not mechanical, it was aerodynamic. As aircraft approached transonic speed, airflow around them changed character. Portions of the airflow accelerated to supersonic speeds, even though the aircraft itself remained subsonic. These localized supersonic regions formed shock waves when the airflow decelerated abruptly. The result was a dramatic increase in drag and disruption of lift. These effects occurred unevenly across the airframe, making them difficult to predict or measure with existing tools. At the time, engineers could not clearly see these forces. Wind tunnel data was incomplete, often distorted by scale effects and turbulence. The industry was reacting to symptoms without understanding the system producing them. This was the environment Richard T. Whitcomb entered. Whitcomb was born in 1921 in Evanston, Illinois, United States. He demonstrated strong aptitude in engineering and aerodynamics at an early age and joined the National Advisory Committee for Aeronautics, NACA, while still a student. NACA was the primary US research organization responsible for solving fundamental aviation problems. Its mission was not to build aircraft, but to understand the physics governing them. Whitcomb was assigned to NACA's Langley Memorial Aeronautical Laboratory, where engineers focused on wind tunnel testing and aerodynamic analysis. Unlike designers working directly on aircraft programs, Whitcomb's role was analytical. He studied airflow behavior, pressure distribution, and drag formation, focusing on why aircraft performance collapsed near transonic speeds. Most engineers believed the drag rise problem could be solved incrementally. They treated wings, fuselage, and engines as separate optimization problems. Whitcomb approached the aircraft as a single aerodynamic system. He examined how airflow accelerated and decelerated over the entire airframe, rather than isolating individual components. This led him to a critical realization. As speed increased, different parts of the aircraft reached transonic conditions at different moments. Thick wing sections and fuselage areas caused local airflow acceleration. When this airflow slowed abruptly, shock waves formed. These shocks increased drag sharply and disrupted downstream airflow. The problem was not localized. It was global. Whitcomb discovered that drag rise was strongly influenced by how volume was distributed along the length of the aircraft. Conventional designs created abrupt changes in cross-sectional area where wings joined the fuselage. These abrupt changes intensified shock formation. His solution was radical. Instead of designing wings and fuselage independently, the aircraft should be shaped so that total cross-sectional area changed smoothly from nose to tail. This required redistributing volume sometimes narrowing the fuselage where the wings were thickest, producing a distinctive waisted shape. This principle became known as the area rule. The area rule did not rely on more power, new materials, or complex control systems. It relied on reshaping the aircraft to control how air accelerated and decelerated around it. When applied correctly, transonic drag was reduced dramatically and shock formation was delayed. Whitcomb validated the concept through extensive wind tunnel testing. The results were consistent and repeatable. Aircraft models shaped according to the area rule experienced far lower drag near transonic speeds than conventional designs. The improvement was not marginal, it was decisive. Initially, the idea faced skepticism. The required shapes appeared inefficient and counterintuitive. Some engineers resisted the concept because it challenged established design practices. Flight testing resolved the debate. Aircraft modified to follow the area rule demonstrated immediate and substantial performance gains without increased engine power. By the early 1950s, Whitcomb's work began influencing frontline aircraft programs. Designs that had previously struggled near the speed barrier became capable of reliable high-speed flight. The solution did not come from brute force, but from understanding airflow as a system. Richard T. Whitcomb did not invent a faster engine or a new material. He removed an invisible constraint that had limited aviation progress. By redefining how aircraft interacted with air at high speed, he reshaped aviation before many designers fully understood the problem they were facing. The true test of Richard Whitcomb's work did not occur in wind tunnels. It occurred when his ideas were applied to real aircraft, operating at the edge of the transonic regime. At the beginning of the 1950s, US military aviation faced an urgent problem. Jet fighters were powerful enough to approach Mach 1, but their airframes were not designed to manage the aerodynamic consequences. Performance losses were severe, and strategic programs were at risk. One of the most prominent examples was the Convair F-102 Delta Dagger. Designed as a supersonic interceptor, the F-102 consistently failed to exceed Mach 1 in early flight tests. Despite powerful engines and advanced delta wing design, the aircraft suffered from extreme drag rise near transonic speed. No amount of thrust solved the problem. The program was approaching cancellation. Whitcomb's area rule provided a solution. By reshaping the fuselage to smooth the distribution of cross-sectional area, particularly narrowing the fuselage where the wings were thickest, engineers dramatically reduced transonic drag. The modified aircraft, informally referred to as the Coke bottle configuration, showed immediate improvement. The F-102, previously unable to reach its design speed, became reliably supersonic. This was not an incremental gain. It was a transformation. The aircraft's engine, wings and materials had not changed. Only the shape had. The success of the F-102 validated Whitcomb's theory under real-world conditions. It also sent a clear message throughout the aerospace industry. The transonic barrier was not a hard physical wall. It was an aerodynamic design problem. Aircraft that failed to respect airflow behavior would remain trapped below it. Following this breakthrough, the area rule was rapidly adopted across multiple aircraft programs. Supersonic fighters, bombers, and reconnaissance aircraft were redesigned or refined to incorporate smoother volume distribution. The principle became foundational rather than optional. Whitcomb's influence extended beyond fuselage shaping. His work altered how engineers approached aerodynamic testing and validation. Designers could no longer rely solely on component-level optimization. Wings, fuselages, and engine nacelles had to be considered as part of a single aerodynamic system. Changes in one area affected airflow everywhere else. This systems-level perspective changed aircraft development timelines. Wind tunnel testing became more precise and more central to design decisions. Engineers focused on pressure distribution, shock formation, and drag rise behavior across entire airframes. Performance was no longer evaluated only at cruise or top speed, but across transitional regimes where aircraft spent significant operational time. The strategic implications were substantial. Supersonic capability became reliable rather than experimental. Aircraft could transition through transonic speed without unpredictable control loss or excessive fuel penalties. This reliability mattered as Cold War requirements emphasized rapid interception, long-range penetration, and sustained high-speed flight. Whitcomb's work also influenced bomber and reconnaissance aircraft. High-speed platforms such as the B-58 Hustler and later designs relied on refined aerodynamic shaping to operate efficiently near Mach 2. Again, performance gains came not from raw engine power alone, but from controlling airflow behavior at critical speed ranges. Importantly, Whitcomb did not claim that the area rule solved all aerodynamic problems. It addressed a specific limitation related to compressibility effects and shock-induced drag. Other challenges, structural heating, stability, propulsion integration, remained. But by removing one of the most severe constraints, his work allowed engineers to focus on those problems without fighting a losing battle against drag. Another significant aspect of Whitcomb's contribution was its timing. The area rule emerged just as jet propulsion matured enough to exploit it. Had it appeared earlier, engines may not have been capable of reaching transonic speeds reliably. Had it appeared later, multiple aircraft programs would have failed unnecessarily. The alignment of insight and opportunity was critical. Despite its importance, Whitcomb's contribution remained largely invisible outside engineering circles. Aircraft were celebrated for speed records and combat capability. The aerodynamic logic that made those achievements possible remained embedded in design standards rather than public narratives. Within NACA, Whitcomb continued refining aerodynamic theory. His work influenced not only military aircraft, but also future research directions that would later transition into NASA's mandate. Understanding airflow behavior at high speed became a foundational discipline rather than an experimental curiosity. By the mid-1950s, the transonic crisis that had stalled aviation progress only a decade earlier was largely resolved. Aircraft routinely operated through speed regimes once considered unstable or unreachable. This shift did not occur because engines became infinitely stronger. It occurred because engineers learned how to shape air rather than fight it. Richard T. Whitcomb's work demonstrated that performance ceilings are often artificial. They emerge not from physical impossibility, but from incomplete understanding. By revealing how shape governs airflow behavior at high speed, he enabled aviation to move beyond a barrier that power alone could not break. This change did not happen in combat. It happened in laboratories, wind tunnels, and design offices. But once implemented, it defined the speed, reach, and reliability of modern military aviation for decades to come. Richard Whitcomb's impact on aviation did not end with the area rule. In fact, his most influential work came after the transonic barrier had been broken. Once aircraft reliably crossed Mach 1, new aerodynamic problems emerged. Supersonic flight introduced severe efficiency losses, stability challenges, and fuel penalties that threatened to limit the practical value of high-speed aircraft. Once again, Whitcomb focused not on engines or materials, but on airflow behavior. As aircraft speeds increased, engineers noticed that drag continued to rise sharply even when designs complied with area rule principles. Supersonic aircraft were fast, but inefficient. They consumed large amounts of fuel, limiting range and payload. Military planners required aircraft that could fly fast and far, not just fast for short bursts. Power alone could not meet these demands. Whitcomb identified that the problem lay in how shock waves formed and interacted across the aircraft at supersonic speed, observed that traditional straight wings and conventional shaping produced strong shock systems that increased drag dramatically. These shocks wasted energy and destabilized airflow, particularly at cruising speeds above Mach 1. His solution was counterintuitive. Rather than making wings thinner or sharper, Whitcomb introduced the concept of the supercritical airfoil. This design delayed shock formation and reduced shock strength by reshaping the wing's pressure distribution. The upper surface was flattened and the maximum thickness was moved aft. This allowed airflow to remain smoother at higher speeds before compressibility effects became dominant. The result was a significant reduction in drag at high subsonic and transonic speeds, with benefits extending into the supersonic regime. Aircraft could cruise more efficiently, burn less fuel, and maintain stable control without sacrificing speed. This was not a marginal improvement, it fundamentally changed how wings were designed. Once again, the breakthrough did not require new propulsion systems. It required understanding how air behaved when pushed toward its limits. The supercritical airfoil proved especially valuable for aircraft operating near Mach 1 for extended periods. Strategic bombers, transport aircraft, and later commercial airliners all benefited from the concept. Fuel efficiency improved, range increased, operational costs decreased. The same aerodynamic insight that enabled military performance also reshaped civilian aviation. Whitcomb's work blurred the line between military and civilian aerospace engineering. His solutions addressed universal problems of airflow, not mission-specific constraints. This is why his influence persisted long after specific aircraft programs ended. Within NASA, Whitcomb became a central figure in aerodynamic research. He was known for challenging assumptions, questioning established models, and relying heavily on experimental data. Unlike many theorists, he trusted wind tunnel evidence over elegant equations. If data contradicted expectations, he followed the data. This mindset influenced how NASA approached aerodynamic research. Experimental validation became paramount. Flow visualization, pressure mapping, and systematic testing replaced reliance on simplified analytical models. Aircraft design became more empirical, more disciplined, and more grounded in observed behavior. Whitcomb's contributions also shaped stealth and high-efficiency aircraft indirectly. While stealth design focuses on radar behavior rather than airflow, both disciplines require precise control of shape and surface interaction. The idea that shape governs system-level performance became a guiding principle across aerospace engineering. Despite his enormous influence, Whitcomb remained largely unknown outside professional circles. He did not design aircraft that carried his name. He did not lead manufacturing companies. His work existed beneath the surface, embedded in design standards, airfoil databases, and aerodynamic guidelines used worldwide. This invisibility is precisely why his impact was so broad. Engineers across multiple generations applied his principles without needing to rediscover them. Aircraft evolved faster because fundamental problems had already been solved. By the late Cold War period, aircraft routinely operated at speeds, ranges, and efficiency levels that would have been impossible without Whitcomb's work. Supersonic fighters, long-range bombers, and efficient transports all depended on aerodynamic principles he helped establish. Importantly, Whitcomb demonstrated that technological barriers are often misidentified. Engineers initially believed engines were the limitation. When engines improved, airframes became the limitation. When structures improved, airflow became the limitation. Whitcomb showed that progress required identifying the real constraint rather than amplifying the wrong solution. His legacy is not a single aircraft or a single discovery. It is a method of thinking. Understand the system, measure reality. Let airflow, not assumption, guide design. Modern aviation still operates within the framework Whitcomb helped build. Every aircraft that crosses transonic speed smoothly, every wing optimized for efficiency rather than brute force, and every design shaped to manage airflow rather than fight it, carries his influence. Richard T. Whitcomb did not make aircraft faster by adding power. He made them faster by removing resistance. He did not defeat the sound barrier by force. He redefined the rules that governed it. That quiet shift from fighting physics to shaping it changed aviation permanently.